So an exact ODE is one that can be written in this form, where capital M and capital N are functions of both x and y. That's your independent variable and your dependent variable. I know I've been using t most of the time as the independent variable. The only reason you might use x instead of t is just conventionally, if the solution to your ODE is more likely to be the solution to some like geometric problem in the xy plane, where x and y kind of represent spatial dimensions, you would use x. If your ODE is a model of like some physical process that proceeds over time or some economic model that proceeds over time, then we would use t. But it doesn't really matter, right? Mathematically, all the symbols are the same. For it to be exact, you have to be able to write your ODE in this form, and this has to be true as well. This criterion has to be true, which is to say the partial derivative of that m function with respect to y has to be equal to the partial derivative of that n function with respect to x. Sorry, it's an x. So different notation, right? The one I typed out is Leibniz notation for partial derivatives. Over to the right, that's Lagrange notation for the partial derivatives. So if you see the subscript, you know what that means. Everybody was in Cal 3, right? Okay, so you've seen that before. The way that I remember this, the m's and n's and stuff, is first of all, m appears alphabetically, m and then n, in the ODE. Second of all, the only way I could write this and form an English word is if I have the m and the y together. My. And then n and x is the remaining stuff. So you have to memorize that, but I'm trying to give you memorization tricks. And I meant to give you examples, but I forgot to put in examples. Another thing you remember from Calculus 3 is when we talked about the total derivative of some function with respect to a variable. Like if I have a function psi, and that's the Greek letter psi, if I have a function psi and it's a function of two variables, x and y, then the total derivative of psi with respect to x is going to be the partial derivative of psi with respect to x plus the partial derivative of psi with respect to y times the derivative of y with respect to x. So it gets some contribution from the partial derivative with respect to x. But again, it's just a partial derivative. It doesn't tell the whole story. The remainder of the story comes from the contribution we get from the change in y. And the change in y happens because y changes with respect to x. So this is an this is an important identity that we talked about more in Calculus 3, but remember that. Again, same definition for exact ODE. This is the theorem that says the solution to an exact ODE is going to be the psi function, psi of x and y, where we set it equal to c. This equation is the general solution to an exact ODE. And in this solution, psi is any function that satisfies these two criteria, okay? I need it so that the partial derivative of psi with respect to x is equal to the m function from the original ODE, and the partial derivative of psi with respect to y is equal to the n function from the original ODE. This is also something you have to memorize, but again, the way I remember this is that it's the opposite. Previously, I had m with a subscript y, And so I need psi with a subscript x. And previously I had n with a subscript x, and so now I have psi with a subscript y. So just remember that it's opposite when I'm taking partials with respect to psi. So why would that be true? How could I solve any exact ODE with some function psi and setting it equal to a constant? Well, the proof here is saying with respect to x. That would be the partial of psi with respect to x plus the partial of psi with respect to y times the derivative of y with respect to x. And if psi is any function that satisfies these criteria, then the partial of psi with respect to x is m, and the partial of psi with respect to y is n, and dy dx is y prime. Now, in my original ODE, my exact ODE requires that m plus ny prime is equal to 0. So, in other words, my ODE just requires that the derivative of psi with respect to x is equal to 0. And if we set my function psi equal to a constant, then the derivative of a constant is equal to 0. So now we know that the solution has to look like this function psi equal to a constant. We just have to find psi, and the difficult part of psi, or finding psi, is that we need its partial derivative with respect to x to be this m from my original ODE, and we need the partial with respect to y to be equal to n from the original differential equation. So that's our goal, is to find such a function. And it turns out that I could only find a function like this that solves an ODE like we were talking about if I'm looking for a solution that's analytic. So I'm looking for an analytic function psi. I can only find an analytic function psi if this is true. And the reason is because for an analytic function, the partial derivative of psi with respect to x and with respect to y, which means I take the partial derivative of psi with respect to x and then take the partial derivative of that with respect to y. That's equal to what I would get if I take the partial of psi with respect to y and then take the partial of that with respect to x. In other words, the order doesn't matter when I take a mixed partial derivative. That was another thing we talked about a lot in Calculus 3. It doesn't matter if I take the partial with respect to x first or with respect to y first, it has to be the same. And since m is just the partial of psi with respect to x, and then I take the partial with respect to y, that should give me the same thing as if I have the partial of psi with respect to y and then take another partial with respect to x. So this is why you'll notice this is a criterion. This is the criterion for what it means to be exact. If your ODE doesn't fit this criterion, then you won't be able to find a function psi that works, right? It's not an exact ODE. Okay, so finally the process. How would I actually find this solution? Well, step number one is we're going to say the function psi is going to be the antiderivative of m with respect to x. And that should make sense because the partial of psi with respect to x is equal to m, and so I should just take the antiderivative with respect to x. I have a little plus h of y, where h is just a function of y only, because if psi has some terms that are only a function of y, well then when I take the partial of psi with respect to x, those are all going to go away and go to 0. They won't appear in the capital M function, right? And so I've got to account for this little part. Then we write down the following equation. I set the partial of psi with respect to y equals n, which means I've already got this guesstimate of what psi is. And when I take the partial of this with respect to y, and I set it equal to n, I'm going to get an equation, and it's going to allow me to solve for h prime. And then in step 3, we find h by taking the antiderivative of h prime with respect to y. And in step 4, I just set psi equal to c. This is my solution. So let's try it. Determine whether the ODE is exact. If it is exact, then solve it. And so for an exact ODE, we have m plus ny prime equals 0. And if it really is exact, that means my is equal to nx, where those are supposed to be subscripts. Those are partial derivatives. I'm not trying to multiply. My issue with Lagrange notation is sometimes it's hard to tell whether I'm doing m times y or the partial of m with respect to y. But those are supposed to be partial derivatives. Well, what is m? What is my function capital M in this example?
Would be 4y.
It's part of it.
2x plus 4y.
There you go. Yeah, I want my ODE to look like this, where I have m plus n times y prime equals 0. And so the m part is the part that does not multiply y prime, which is going to be 2x plus 4y. What's the partial derivative of m with respect to y? 4. Okay. What is the n, capital N part of this ODE? 2x is part of it.
Do you put the y prime with it? Is it? Would it be 2x y prime?
No, it's the thing that multiplies y prime. There you go. Yeah, because I need the right side of the ODE to be 0 here. So it's going to be 2x minus 2y. The partial of n with respect to x is what? 2. So is this an exact ODE? I would need this to be equal to this, and so this is not exact. Okay. Same thing. Determine whether the ODE is exact. If it is, then solve it. Number 1 is, let's rewrite this ODE as m plus ny prime equal to 0. And then after we rewrite it like that, we'll double check to make sure the partial of m with respect to y is equal to the partial of n with respect to x. So what is going to be my capital M?
X squared plus 2 minus 2x.
Very good. What is the partial of capital M with respect to y? Negative 2x. All right, what is capital N? Don't forget the plus 3, yeah. Otherwise you're good. And what is the partial of capital N with respect to x? Very good. And look at that. If I wanted this to be true, my criterion for exactness, now we found that negative 2x is the partial of n with respect to y, and negative 2x is the partial of n with respect to x. So this is exact. And now that we finally found an exact ODE, we can solve it. In my solution method for solving this thing, we are going to look at the function psi. We want to find psi such that the partial of psi with respect to x is equal to m, and the partial of psi with respect to y is equal to n. So we start off by saying that psi is going to be the antiderivative of m with respect to x plus some function of only y. Since m is 3x squared plus 2 minus 2xy, that antiderivative with respect to x is going to be this. And when you're solving an exact equation, you don't have to write plus c when you take an antiderivative. The reason for that being is that whenever I go to write my final answer, the final solution to this ODE, or the general solution to the ODE, is going to be psi equal to a constant. And this is the arbitrary constant that's going to take care of all of my constants of integration. And so for the purpose of solving an exact ODE, it's not important for me to write plus c anywhere. The next part of this is I need to also guarantee that the partial of psi with respect to y is equal to n. And that means I can start with this and take the partial with respect to y of x cubed plus 2x minus x squared y. And set that equal to n, where n is, 6y squared plus 3 minus x squared. Oh, and I forgot h of y. Sorry. Got to squeeze in a plus h of y there. Okay. So far, so good? So what is the partial derivative of all of this stuff with respect to y? All the stuff inside the parentheses. Well, the partial of x cubed with respect to y is 0. The 2x goes to 0. And this becomes negative x squared. And the partial of h of y is going to be what we call h prime of y. So the prime indicates the derivative because this is a function of only y. That's a derivative with respect to y. On the right side, we still need this to be equal to 6y squared plus 3 minus x squared. That means h prime of y must be equal to 6y squared plus 3. And that means h of y is just going to be the antiderivative of h prime of y with respect to y. So what's h of y? Yeah, take an antiderivative, so it's going to be 2y cubed plus 3y. And again, I don't have to write plus c when I'm solving for an exact ODE. Just because when I go to write my final general solution, I set psi equal to c, and that c is going to take care of sort of the arbitrariness, the arbitrary constant part. But now I go back here and I say, well, I had that psi is equal to all of this stuff, that expression, plus h of y, and now I finally figured out what that h of y is. So I can finally write an entire expression for psi. And that means psi is equal to x cubed plus 2x minus x squared y plus 2y cubed plus 3y. And to find the general solution to my ODE, I just have to set this equal to 0. Okay, let's check our answer. And we can pull up Desmos and pull out our direction field. And in here, I'm gonna have to solve for y prime to put it into Desmos. So that's not too crazy. It's gonna be negative 3x squared minus 2 plus 2xy divided by 6y squared plus 3 minus x squared. So I get this nice direction field representing my ODE. And then to put in the general solution, type it in just like I got it, which is x cubed plus 2x minus x squared y plus 2y cubed plus 3y equals c. And then to solve the initial value problem, I've already got this explicitly in terms of stuff equals c. I just have to turn all of these x's into x zeros for my initial value, and all my y's into y zeros. And now, after that, oh, and I might also have to write it in Desmos as c equals. Yeah, now it's happy. Okay, so we double check our answer by saying, I've got my orange solution curve that passes through my green initial conditions. And wherever I decide to move my initial conditions, I always see that the orange curve is passing parallel to any direction lines. This is kind of nice. So, whenever we were talking earlier in the lecture about like, when do you use X or when do you use T? First of all, it doesn't matter, right? The math works the same whether it's X or T. Second of all, the reason somebody might use X instead of T is because this is a real geometric solution, right? This is a curve that fits the ODE, but this is not a function in orange here. Like this one value of X has multiple values of Y. And so if you think about how this system is progressing, in your independent variable, you're going from left to right, you're going from left to right, you're going to left to right, and then like you get to this point, and like if this were the time axis, the solution no longer exists after some point in time, and so it doesn't really represent what we typically would think of as a time-dependent system. Because you can't go backwards in time. At least I can't. Okay, so when we get to this point, you say, how is my test going to look, right? When you all come to class on Monday and you have your test. Your test is going to probably have a question about verifying a solution to an ODE. Like I might give you like a second order ODE and a solution, and you just have to tell me whether or not the solution is correct. Or maybe for that kind of question, I could give you like a multiple choice question, A, B, C, D, E, where I give you different possible candidate solutions, and you have to plug that into the ODE to figure out if it's a solution. So we did some verifying solutions on our first day. Then we also did classifying ODEs. There was a time when we weren't solving ODEs, we were just classifying them based on the adjectives and the vocabulary terms we learned. There'll be a question about classifying ODEs. There's going to be a question either about drawing a phase line or a direction field or a phase portrait as a way to visualize an ODE, so be comfortable with drawing those by hand. And then for the remainder of the test, I have 6 different types of ODE I could give you, right? The 6 different solutions we've kind of come up with so far are like separable ODEs, first order homogeneous ODEs that can be made separable by setting u equals y divided by x. Linear ODEs and Bernoulli ODEs, where Bernoulli ODEs can be made linear with the substitution u equals y to the power 1 minus n. And then exact ODEs, like we just did, we just worked. And then also, I could give you an equation that is not exact, but could be made exact. And so you should be able to recognize those and be able to sort ODEs by those categories. So that way you know what solution method to use. I'm not going to tell you what solution method to use on your test, but you've got to figure out which solution method to try. Okay, so let's talk about ODEs that can be made exact. They're not exact right away, but we can make them exact by multiplying the entire ODE by an integrating factor. And so my integrating factor mu is potentially a function of x and y. And if I were to do this, it would look like mu of m plus mu of n times y prime equals 0. Because 0 times mu is still 0. So that's what it looks like to multiply my entire ODE by mu. And then we would say, I'm looking for a solution psi such that the partial derivative of the partial derivative of psi with respect to y is not just equal to m anymore. No. N. It'd be n. It's not just equal to n anymore, it's going to be equal to mu times n. And instead of having my partial of psi with respect to x just be equal to m, I want this to be equal to mu times m. The partial of m mu, or mu m, with respect to y is equal to the partial with respect to x of mu n, because that would be the condition for exactness of this ODE. What is the partial with respect to y of mu times m? So think about the derivative product rule. The derivative product rule would tell me I take the partial of mu first with respect to y times m plus mu times the partial of m with respect to y. And on the right side, this would be the partial of mu with respect to x plus mu times the partial of n with respect to x. Okay, so let's recap. We multiply our entire ODE by mu because it's not exact and we want it to be exact, so maybe an integrating factor can help. And so we want to find a function psi such that this is true. That way my psi equals c can be the general solution to my ODE. Well, what do I choose for mu? That's still the open question. Well, I need to choose mu so that it makes my ODE exact. And this is now the criterion for making my ODE exact here in purple, is that the partial of mu m with respect to y is equal to the partial of mu n with respect to x. If that's true in purple, then my new ODE, where I've multiplied through by mu, is exact. So actually applying the derivative product rule to this criterion to figure out what mu we're looking for. In other words, mu has to satisfy this. We must choose mu so that it satisfies this condition. Only the sort of problem here is that this is a partial differential equation, considering it has more than one variable. We're taking a derivative with a partial derivative. That is even more difficult than our original ODE. Unless mu is actually just a function of x, or mu is actually just a function of y. So I need to choose mu so it satisfies this black equation. But that's super ugly and gross, and it's going to be impossible to guess a mu that satisfies the exact equation. So you might give up, except that in rare instances, in special occurrences, sometimes this integrating factor is a function of x only, and it's not a function of y. Or in other special situations and special equations, this mu might be a function of y only, and it's not a function of x. Those are the two special cases where this actually becomes a tractable problem. And in the first case, where we have a integrating factor that's a function of only x, this big ugly equation becomes the partial of mu with respect, actually, what is the partial of mu with respect to y? It would be 0. If mu is a function of only x, then it doesn't have any y's, and this partial derivative is 0. So we move on and we say mu times the partial of m with respect to y is equal to the partial sorry, that should be the partial of mu with respect to x times n and then plus mu times the partial of n with respect to x. Nice. So here we go. If I solve for mu, we can finally solve for mu and write mu of x is equal to So this is still a differential equation, but this partial derivative of mu with respect to x is actually a derivative of mu with respect to x, because x is the only variable. But then we get something like mu prime of x times n divided by the partial of m with respect to y minus the partial of n with respect to x. Can rearrange this and get mu prime is equal to this and the solution to this ODE here in blue is that mu of x is equal to the exponential of the antiderivative of, we'll call it f of x dx, where f of x is my minus nx over n. And importantly, I need to make another note here, is that this only works this is only possible if this part is a function of x only. In other words, if you take partial of m with respect to y minus partial of m with respect to x and divide by n, and you have y variables left hanging around, then this can't work. It's not one of those special situations where it can work. The reason being is because we said mu has to be a function of x only. Mu prime then is obviously a function of x only, and what am I multiplying mu prime by? Well, I'm actually dividing mu prime by this whole expression I just wrote down. And so that means this expression has to be a function of x only. If not, I would have y's here and then I would have y's there. So that's something I gotta check. We have to check this criterion to make sure this is a function of x only. Otherwise, we can't use an integrating factor as a function of x. When I do check this, and I make sure that this criterion is true, well then how do I find what that integrating factor is? I would use this formula. This formula says mu of x is equal to the exponential function of the antiderivative of something, and that something is, actually it's exactly the same criterion we just checked a moment ago. And so if I take this antiderivative, and then I take e to the power of the antiderivative of this, that gives me my integrating factor. I can multiply my ODE by that integrating factor and then solve it with the exact method. The other case gives me something similar. Okay, we just talked about the first case. Right, we just talked about this. I'm beginning to prefer the Lagrange notation because it's just faster to write down. Okay, so remember, check this criterion to make sure it's a function of only x, and then you use this formula to find the integrating factor. The second case, I could show you exactly the same derivation, only we assume that mu is a function of y only. And if we assume that mu is a function of y only, then the criterion we have to check is now the partial of n with respect to x minus the partial of m with respect to y divided by m. The difference here is that you multiply by a negative, or you switch the order of subtraction, and then you divide by m instead of dividing by n. And if that's a function of y only, then I can find my integrating factor according to this formula, where the g of y is that thing. So there's two cases in which an integrating factor might actually be useful to us. Once where the integrating factor is a function of x only, and then the second case where it's a function of y only. If the integrating factor had to be a function of x and y, then like I said, you'd be stuck with this partial differential equation that's even more difficult than the original differential equation we're trying to solve, and then you'd just be stuck. But I've got one example of this, of what we can do, and I think in the next 20 minutes we can probably solve this using the method of integrating factors. So let's try it. Consider the following ODE and determine which category it belongs to. If the ODE belongs to one of the latter two categories, find the general solution to the ODE. Okay, so the first thing I do if I see this is I'm trying to rewrite it as m plus ny prime equals 0. In other words, I see like m would be equal to 3x squared y plus 2xy plus y cubed, and n would be equal to x squared plus y squared. So the partial of m with respect to y would be 3x squared plus 2x plus 3y squared. And the partial of n with respect to x would be 2x. So this is clearly not exact. But there's two situations where I might be able to make it exact. Number one, let's check to see if mu is a function of x only. Right? Maybe there's an integrating factor that exists as a function of x only. And that would require, that my minus nx divided by n is a function of x only. And in our case, my minus nx is going to be 3x squared plus 3y squared. And dividing by n divides by 2x, not 2x, divides by x squared plus y squared. So that's 3. And this is a function of x only. So that means it can be made exact. And the way I make it exact is I choose the integrating factor that is the exponential of the antiderivative of 3. In other words, that's e to the power 3x. And now I go back to my original ODE, and I'm going to multiply everything by e to the 3x. So that way, my m is now going to be 3x squared y plus 2xy plus y cubed times e to the 3x. N is going to be x squared plus y squared times e to the 3x. Let's double check and make sure that my is equal to nx. Make sure that my equation is exact now. And the partial of this with respect to y would be 3x squared e to the 3x plus 2x e to the 3x plus 3y squared e to the 3x. I guess I could have just factored out e to the 3x. Oh well. And then over here on the right side, the partial with respect to x would be, have to do the product rule, which would be 2x e to the 3x plus 3x squared e to the 3x. Oh yeah, plus y squared e to the 3x would have partial derivative with respect to x, 3y squared e to the 3x. And it works, right? Now these are equal to each other, so now we have an exact ODE. And now we can proceed by solving my new exact ODE. And to solve an exact ODE, we start off by remembering that the partial of psi with respect to x should be m. So we set psi equal to the antiderivative of m with respect to x plus potentially some function of y. So now we've got to take the antiderivative of m with respect to x. And this is going to be a big, nasty integration by parts, it looks like. And I'll start my integration by parts over here. In an integration by parts with a polynomial factor and an exponential factor, the polynomial gets to be the u. So the u is going to be 3x squared y plus 2xy plus y cubed. And the dv gets to be e to the 3x. I lost my 3 here. There we go. And then I take derivatives of u, and this time they're going to be partial with respect to x. And so I'm going to pretend the y is a constant because I'm taking the antiderivative with respect to x. So pretending y is constant, the derivatives would be 6xy plus 2y. And then another derivative would give me 6y, and another derivative would give me 0. Antiderivatives of e to the 3x would be 1/3 e to the 3x, 1/9 e to the 3x, and 1/27 e to the 3x. So remember, in integration by parts, we pair them up kind of diagonally so that, oh, and don't forget plus, minus 2. I'm going to end up with 1/3 3x squared y plus 2xy plus y cubed e to the 3x minus 1/9 6xy plus 2y e to the 3x plus 6/27 y e to the 3x. And I don't need a plus c because I'm just looking for any function that satisfies these relations. It doesn't necessarily have to be something specific. It's just an integrating factor, right? Well, kind of. You get what I mean. The h of y part is still unknown. And so we remember that the partial of psi with respect to y has to be n. And so we're going to have to take the partial derivative of all of this junk with respect to y. And set that equal to n. Taking partials with respect to y. This is going to be 1/3 3x squared plus 2x plus 3y squared e to the 3x minus 1/9 of 6x plus 2 e to the 3x plus 6/27. What is 6/27? 2/9 e to the 3x plus h prime of y. And that has to be equal to n. And n is, which is x squared plus y squared e to the 3x. That may or may not make things a lot easier, but we actually will get the right solution, so that's good. Thank you for catching that. H prime of y is going to be equal to x squared e to the 3x minus x squared e to the 3x. Okay, so the x squared e to the 3x's are going to cancel. The y squared e to the 3x's are going to cancel. And so I'm going to be left with 2/3 x e to the 3x minus 2/3 x e to the 3x. That's going to cancel. Plus, oh, hold on. I'm getting my pluses and minuses mixed up. Because I'm solving for h prime. So this is going to be negative 2/3 x when I move it to this side of the equation. Oh, but then this would be positive 2/3 x. Okay, so I'm okay. If you mess up two plus or minus signs, sometimes it cancels out and you're fine. Two wrongs make a right. So now I'm moving on to here, where I've got just negative 2/9 e to the 3x, but we move that to the other side of the equation, so that becomes positive 2/9 e to the 3x. Oh, and then it cancels out that one. So what is h prime of y? It's just, it all cancels. It's 0. That is a lot nicer. That saved us from having to do integration by parts, and it saved us from getting the wrong answer. So if h prime of y is 0, I can take the antiderivative, and of course it's a constant, but we don't really have to care about the constant when we're solving an exact equation. So what is psi? Psi is just what we already found then. Let me highlight it for you. Psi is this, but where you see that plus h of y at the end, that's nothing. We showed that it already happens so that the partial of psi with respect to y is n. So that's cool. That happened to be an easy part of this problem. And so whenever I go to write my solution, and I set psi equal to c, I should really try to clean this up as much as possible and do whatever I can to make it look better. And so in the first place, I've got x squared y. And then for these xy terms, I think they cancel. 2/3 negative 2/3. I've got y cubed, or 1/3 y cubed. I've got negative 2/9 y plus 2/9 y, so that cancels. And this is just times e to the 3x. There's my solution. I can't believe how nice that solution turned out. Right? After all that work, it's like kind of crazy when it turns out that simple.